Okay, so we should start. So it's a pleasure to have one of our neighbor from CA, Benjamin Magnelli. So Benjamin is now the group leader at CA of the CosmoStat and Galaxy group laboratory there. So before that, you did your PhD at CEA,
yes.
and then a postdoc at MP Garching, and then a postdoc at Bonn. Before then returning to CA. And before that, I just learned that you actually did your master project here at IP with Brigitte.
Yes.
So you're from here.
2005.
Okay, so Benjamin works
years ago.
Yeah, so Benjamin works on observations in the infrared domain mostly, but not only. You worked on Herschel, Spitzer, ALMA, and James Webb, and you participate to different projects on the James Webb, and you're going to talk about this today. So the floor is yours.
Okay, thanks a lot. So hi everyone, it's a real pleasure to be here. Yes, as Johan said, I was here 20 years ago to do my master in 2005, and I think in 2001 I was at the library here, and I was working at the library. It was weird. So it's a very long time. The building have changed quite a lot. It's much better now. Okay, so today I'm going to speak about the main sequence of star-forming galaxy, and I will try to convince that this new paradigm that have been built over the last 20 years gave us new insight and perspective on massive galaxy formation. Okay, so when you study a galaxy evolution, it's of course a very vast and fascinating topic. And it's very vast because you want to understand the formation of the very first galaxy, only a few 100 million years after the Big Bang, up to the very diverse population of nearby galaxy, the blue spiral, your red and dead elliptical. It's a very complex subject because it involves physical mechanisms that act on a range of a time scale and a range of scale that are very, very large. Of course, you want to understand the formation of the large structure of the universe up to how the stars form in a single galaxy. So it's very, very difficult. And you can have different approach to this problem. And the one that I've used and the people I've been working on are using is more a top-bottom approach, where you try to first understand the key processes that drive galaxy evolution, like the scaling relation. And then as you understand this first-order evolution, you try to step down into more and more complexity into the description of this process. So when you want to approach this, the first thing that you will try to do is to understand when stars are formed in the universe. So that kind of give you the blueprint of galaxy evolution and which time scale, which time of the universe is the most important for you. So what you want to do is a very demographic point of view. You just want to count the number of stars that have been formed per unit co-moving volume in the universe at a given amount of time. What you have to do is that you have to catch, of course, the star formation process. So you are based on the very massive stars, because very massive stars are short-lived. And therefore, if you see their emission, you are sure that you are looking at an instantaneous star formation activity of a galaxy. And what is nice is that massive stars are the ones that dominate the emission of UV photon. So what you do is you look at the UV photon that you receive on Earth coming from galaxies, you count them, you multiply by a conversion factor that people doing stellar evolution will give you, and then you get the star formation activities. And actually, ironically, it's very easy to do that at high redshift, because, of course, at high redshift, the UV is redshifted into the optical and the territory of the Hubble or the James Webb, and therefore, it's quite easy to actually look at this UV emission. It's actually more difficult to do it in the local universe, because in the local universe, you need real UV telescope, and we had only one, which was GALEX. Okay, but so if you do that, you obtain this evolution of the star formation rate density of the universe. But as you might know, stars are formed out of molecular gas that contain also dust. And at the end, these massive stars barely have the time to sweep out the cocoon for which they are formed, and a huge part of this UV photon will be absorbed by the dust. And so you think, okay, I also have to catch this infrared photon, convert them into a bolometric measurement, and get the star formation rate that come from the infrared. And that's what we have been doing. It's quite difficult because you need infrared telescope or mostly in space with Spitzer and Herschel, but of course, ALMA or NOEMA can do this job for you at the highest redshift. And when you do that, you intend that actually what you are looking in the UV is a subdominant. You basically have 10 times more energy coming out in terms of thermal emission from the dust than what you see directly in the UV. So you absolutely need to have this view, this panchromatic view on the galaxy evolution if you want to understand it. Because about 10 times more star formation activity is coming out from the infrared proxy than from the UV. So now if you combine all that, you can see that at a redshift of 3 or 4, we basically have no more infrared emission. It's not that it's not here, it's that our telescope are not deep, cannot provide deep enough observation to probe this infrared emission. So we have to use the UV that we correct from dust attenuation. And if you combine this, you obtain one of the most famous plots over the last 10 years. I'm sure you already have seen it, what we call the Madao plot, which is the star formation history of the universe. And what you learn is that the universe is not boring. It's actually evolved quite a lot. Okay, you have a sharp rise of the star formation activity over the first 4 billion years of the universe. And then since cosmic noon, redshift of 2, since 10 billion years, the star formation activity of the universe have decreased by a factor 10 to 20. Yes. Yeah. I didn't say Lily. Okay. So yeah, we can say Madao and Lily plot, but okay, that's the history, the cosmic history. I don't think it belongs to, that's our cosmic history. Let's put it that way. Okay. And what is very important with this plot is that if you do the integration of this plot, you will obtain the budget of stars that have been formed from a given epoch. And what you will learn is that about 50% of the present-day stars have been formed at high redshift. And this is very important, but that tells you that if you want to understand galaxy evolution, you absolutely need to study the high redshift universe. It's not only fun to do the high redshift universe, it's also very useful because a lot of the galaxy evolution happen actually at high redshift. It is difficult, but we need to build this telescope to be able to decipher how galaxy evolution takes place. Okay, so of course that raises a lot of questions. What triggered this rise and fall of the star formation activity of the universe? What is the higher? Is it higher star formation efficiency or higher gas contents, for example? Okay, so you need to go beyond this simple time scale of the galaxy evolution and try to enter at a given redshift in how star formation activity takes place in galaxy. And so if you do that in the local universe, so you go at a given time, the second big parameter that you want to explore is how star formation will organize as a function, for example, of the stellar mass of the galaxy, which is a proxy also of the gravitational potential of a galaxy. And if you do that, you obtain this type of plot where you see two things. First, you see kind of bimodality. So you have your star-forming galaxy that are here, and then you have your red and dead quiescent elliptical that are here. And as I said, this bimodality is what's already known from the color magnitude diagram. And in a sense, the star formation rate stellar mass plot is a simply physically motivated reprojection of the well-known color magnitude diagram, where the color is a proxy of the star formation, and the magnitude in the R band here is a proxy of the stellar mass. But now you have many more bands, so you can do a much more precise measurement of the real star formation rate and the stellar mass. And what is important is that indeed you can see really the bimodality. You have your blue cloud here, and you have your red dead galaxy. And what is important with this physically motivated reprojection is that you can look that there is a clear correlation between the star formation rate and the stellar mass of star-forming galaxy. This is not so incredible. That's just a scaling relation. Bigger have bigger star formation activities. But what is fascinating and why we call that the main sequence of star-forming galaxies is that the dispersion of this correlation is only of a factor 2. So that means if you give me the stellar mass of a galaxy, I can predict the star formation like this galaxy within a factor 2. And that tell you that the star formation history of a galaxy cannot be very super stochastic, that change on a very short time scale, because that will have tendency to broaden this relation. And that tells you that somehow, most likely, the star formation activities of main sequence galaxies is kind of self-regulated. Yes? Yes. So you look, for example, here where you are not too much affected by the main sequence, you can see a Gaussian distribution. And then here, even if you do a slice here, you will have two Gaussian distributions that you can separate. And the dispersion is relatively constant of 0.3 dex at all stellar mass. Okay, and so it tells you something that most likely most of the star formation activity in the local universe is in a secular mode of star formation, not triggered by major merger. And actually, the Milky Way is falling right onto the main sequence. So what's happened at higher redshift? So if you do the same game, and we could do that thanks to Spitzer and Herschel, you will observe this main sequence. Of course, it's not as well characterized than in the local universe, but you will observe this main sequence of star formation all over the redshift you can probe. And now we can even go up to redshift of 4. So you have this tight correlation with more or less the same dispersion than what we call in the local universe. What changed the most is actually the normalization. So at higher redshift, the main sequence is still in place, but its normalization is 10 times higher than what we observe in the local universe. And that explains why the star formation rate density is 10 times higher. So in a sense, that seems to tell you that the mode of star formation activity at a redshift of 2 at cosmic node is not significantly different. You don't need to invoke more major merger or starburst. It seems that you will have the same mode of star formation at high redshift, but why does at a given mass it's 10 times higher is still open, of course. Now, if you make the math, of course, most of the star in the local universe have been formed inside this main sequence. So if you are able to describe what regulates star formation in this galaxy, you will better understand about the bulk of the star formation activity of the galaxy evolution. Now you can ask, what about starburst? And we know that in the local universe, you have galaxies like ARP-220 that are starbursting. And the official, the historic definition of a starburst, that means your instantaneous star formation activity is much higher than your average star formation activity. And this is very difficult quantities to measure, because it's difficult to measure the past star formation activity of a galaxy. But now that you have the main sequence, you kind of know what is the average star formation of a galaxy at a given redshift and of a given mass. And so in a sense, by definition, if you are way above the main sequence, you must be a starburst. And actually, if you look at the distribution of galaxy, indeed, you see again a tail of distribution of galaxies that are way above the main sequence that we call starbursting galaxy. Their contribution to the total budget of star formation in the universe is not so large. It's between 10 to 20%. But of course, they might have a big contribution for example, the formation of quiescent galaxy. So that is nice. By looking just at the star formation rate and the stellar mass, you seem to see that. But of course, you need to confirm that at high redshift, indeed, main sequence galaxy look similar than the Milky Way that is also a main sequence galaxy. What we did is, for example, to look at the morphology of galaxies. Okay, so you go at a given star formation rate and stellar mass. You don't care if there is a main sequence or not. You measure the morphology of galaxy, and you just plot here the average Cerseic index, whether or not it's n equal 1, like a disk, or if it's a bulge, like n equal 4. And this is what you obtain. And you can clearly see where is the main sequence. You don't need to know that there is a main sequence, but you can see it. Then you plot the main sequence, and indeed, at z equal 2, the main sequence at a given star stellar mass is 10 times higher than in the local universe. But still, the galaxies that populate this main sequence still look like disk. Okay. Before, we were thinking that maybe the higher star formation activity at z equal 2 is triggered by major merger. But it was clear that it's not the case. Main sequence galaxy have 10 times higher star formation rate, but they still look like disk. And you can clearly see that at z equal 2, the Hubble sequence is already in place, because you can see your red dead quiescent galaxy here. Another result, I would say great, because of course it's mine, so maybe I should not say that too much, but was we could measure the dust temperature of this galaxy thanks to Herschel. Okay, and the dust temperature is a proxy of the condition of the ISM and also a proxy of the star formation efficiency of your galaxy. How much stars you form per unit dust and therefore per unit gas. And you can see that again, if you measure the mean dust temperature of galaxy and you don't care whether or not there is a main sequence, you just plot the temperature. You see clearly an iso temperature that follow perfectly the main sequence. So that means that the galaxy that is here, that's forming star about 10 times lower rate than galaxies that are more massive, that are still on the main sequence, have exactly the same ISM condition and the same star formation efficiency. Okay? So in a sense, it seems that galaxies have a universal break of star forming region. And when you are 10 times more massive and you are on the main sequence, you have 10 times this number of break. Okay, so it seems that you have the same star formation efficiency. And now, thanks to ALMA, but also to NOEMA, we can actually quantify that. We can measure the gas and the dust content of this galaxy. And we can see that indeed galaxies at higher redshift are containing 10 times more molecular gas than galaxies in the local universe. So in a sense, you don't have to invoke a different star formation efficiency to understand the increase of the star formation density of the high redshift universe. You simply have to understand why galaxies at a redshift of 2 contain 10 times more molecular gas than the local universe. Now, what is very striking is that if you take the molecular gas reservoir of galaxies and you divide by their star formation rate, what you obtain is what we call the depletion time. So the amount of time their molecular gas reservoir will be totally depleted by their current star formation activity. And what you find is that it barely changes as a function of the redshift. And it's always way below 1 gigayears. So that means that if you take the full star-forming galaxy population at z equal 2 and you let them go at z equal 1.8, they are all gone because they don't contain any more gas. And so we know they are still there. And therefore, that's an indirect proof that you need to somehow replenish their molecular gas reservoir constantly. And so that gave rise to, I would say this new paradigm is maybe a bit too much to say that, but especially people that have been looking at the molecular gas, is that we know that you have a tight and time-independent shape of the main sequence that kind of tell you that the star formation activities of galaxy is relatively smooth and goes on for gigayears. But at the same time, we just said that, okay, you don't have the molecular gas reservoir to sustain this star formation activity over several gigayears, and therefore, you absolutely need to replenish this molecular gas reservoir. Most likely from the cosmic web, and that's what people doing simulation have been telling us, is that you have the accretion from the cosmic web of fresh gas onto the galaxy that need, of course, to cool down and reach the galaxy, but you have this reservoir. And so it seems that the higher star formation higher star formation activity of high redshift galaxies is simply due to the fact that the tap coming from the cosmic web, so that means the amount of material going inside the galaxy is just more open. And as you go to lower and lower redshift, the tap is diminishing, you are closing it, and therefore the star formation activities of galaxy decrease. And so this gave rise to this bathtub model where with only one simple differential equation that is telling you how the molecular gas reservoir vary as a function of how much you open the tap, how much you use it with star formation, and how much you do the outflow. And in a sense, galaxy seems to be in an equilibrium between the accretion, the star formation, and the gas outflow. That's what people have been calling gas regulator model. And if you go to the simulation and you take the value of the accretion onto galaxy, this thing from simulation, and then you can actually reproduce quite simply the localization of the main sequence, the slope of the main sequence, and how it varies as a function of the redshift, simply with this input parameter. Now, I would say recently we have something that I find it relatively neat to try to support this thing, is that I told you that the main sequence is a nice correlation, and I didn't mention the slope. But what we know is that actually in the local universe, what we see is that it has a slope of 1, and then you have what we call a bending of the main sequence. Okay, it seems that the star formation rate doesn't increase anymore as you go to higher stellar mass. And this bending disappeared as you go to the higher and higher redshift. And what is, again, this is more indirect, is that if you translate the bending mass, the stellar mass, into a halo mass using standard conversion between stellar mass and halo mass, then you actually end up with this value. And if you plot that onto this decal paper where you divide the place where you can actually have accretion onto a halo, and as you go to more and more massive halo, if you have accretion of gas onto the halo, actually you have a shock that happens, and the gas doesn't really fall into the halo. Okay, that's what they call the division between cold stream in hot medias and hot accretion that come from simulation. And you can see that this stellar mass, the bending of the main sequence seems to follow this thing. So that will be another kind of support that indeed, as you pass the fact that you cannot accrete any more gas onto the halo, as you go to a higher stellar mass, you start already decreasing the accretion, and therefore your star formation activity cannot increase as you go to higher stellar mass. Okay, so this new framework, and I would say now most of the galaxy evolution study will always not look, for example, at galaxy in terms of absolute star formation rate or stellar mass, but really whether or not you are on the main sequence at your stellar mass or above the main sequence or below. So in a sense, now galaxy evolution study are usually made with respect to the localization of a galaxy with respect to the main sequence. But it doesn't tell you everything, of course. I mean, I still didn't tell you how you drive the structural evolution of galaxy, what control the dispersion of the main sequence. We said that we measure a dispersion of 0.3 dex, and we believe that this dispersion is not driven by the measurement. It's driven by its intrinsically a dispersion of 0.3. And so now you have gas regulator models that try to explain this dispersion based on the stochasticity. So that means how much the star formation history vary at a given time scale around an average value. Of course, I didn't speak about the role of environment, and I will try in the outlooks. I think is one of the big things that we can do now with Euclid and SK and future visibility that allow us to probe deep, to obtain deep survey of wide sky area. But it's still very difficult because when you want to look at high redshift galaxy, you need very deep observation, and usually that's end up being small survey. And so it's hard in those small survey to have many cluster, many group, many filament, many void, many field, and therefore it's difficult for us to disentangle the role of environment, while it seems to be critical because if star formation is mostly driven by the accretion from the cosmic web, obviously the environment should be a big parameter. I didn't speak too much about the role of major merger. What is their role in galaxy evolution? And of course, we think they are linked with how you create this red and dead ellipticals, okay? And the last thing is all I showed that are more studies that concentrate at a redshift below z equal 4. So in the last, let's say, 10, 12 billion years, in the last 10, 12 billion years, and what's happened in the very, very high redshift. Okay, so I will not have the time, of course, to speak about all that. So I selected the 3 topics that I think we've made progress recently. And of course, if you want to speak about other things, we can discuss after. So the first thing is what drives the structural evolution of a star-forming galaxy? Yes? Yes, I think this is because in a sense, people doing simulation were telling that to us, and this is great, but I mean, somehow we need to verify this by observational. So I think now we have observational evidence that indeed the cold accretion onto the halo play a major role into galaxy evolution. But people doing simulation knew that, but we need also to verify that. Sometimes we cannot. Okay, so the structural evolution of star-forming galaxy. So it's well known from Hubble and Kendall's observation, and now with James Webb even more, that if you look at the size of galaxies as a function of the stellar mass and at different redshift, you will end up with what we call mass-size relation for star-forming galaxy here in blue, and mass-size relation for quiescent galaxy. And if you look at the slope of this relation for star-forming galaxy or for quiescent galaxy, you can see that they are radically different and that they also evolve as a function of the redshift. So this is the z equals 0 slope, and this is the z equal 2. And so if you try to connect progenitor and descendant from one redshift to the other, you have to use some so abundance matching technique. What you end up is that the fact that star-forming galaxy must have experienced a significant growth of their size as they evolve in mass, so their disk is growing in size. And also, to become quiescent, they must go through a compaction phase, because at any redshift, even if you have progenitor bias, the quiescent galaxy have a de Vaucouleurs profile and are much smaller. And so, of course, we want to understand what is the mechanism. So people will say, okay, you have inside-out growth from the disk. So that means you deposit a bit more star formation activity in the outskirt. And for the compaction, you can have wet or dry compaction. But of course, we want to understand that. And so far, it was very difficult, because to see this mechanism in place, you need, again, to look at the star formation activities. So in the sense, the differential of this plot. And the star formation is, again, you need infrared observation. No way you do that with only UV corrected from attenuation. And therefore, you need air shell, for example, or Spitzer, but it have a resolution that all those galaxies are unresolved spatially with Spitzer and air shell. And therefore, you can play with ALMA. But ALMA has a very, very small field of view, and it's still very expensive to detect only one galaxy with ALMA. And therefore, you could do that for, let's say, a few hundred galaxies. But all the studies that I show need thousands and thousands of galaxies. And so now with James Webb, we can do that, because James Webb has one of the instruments is MIRI, so it's a mid-infrared instrument that look at the dust emission in the mid-infrared, has a relatively good spatial resolution, and can do that for thousands of galaxies. Okay, and so we could look for the first time with MIRI, which also have been significantly developed at CEA. We could look at the spatial, at the star-forming component of galaxy, in a sense, and look at the differential. So what did we find with this MIRI observation from James Webb, so the very deep observation, is we could compare the position angle, the size, and the Cercic index of the stellar component here on the x-axis. And on the y-axis, I put the same thing, but as estimated from MIRI. So that means the star-forming component, which is the dominant star-forming component, because most of the star formation is dust obscured. And you can see that the position angle meet perfectly, or at least to first order, and then you have the size that seems to match. And the Cercic index is a bit more dispersed, but overall, what you found is that the star-forming component also look like a disk. It have an n between 0.7 and 1, and it have more or less the same size than the stellar component, and it's also a line on the stellar component. Okay, so now for the first time you can see the real growth of the morphology with this measurement. So it seems that the star-forming components also look like a disk of the same size than the stellar component. Now, if you go a bit more in details and you look at the Cercic index and you look as a function of the stellar mass, the optical is in orange here and the star-forming Cercic index is in black. What you can see is that the optical is rising as you go to higher stellar mass, while the one of the star formation doesn't rise, okay? So the one of the stellar component rise because we know that as you go to higher stellar mass, the bulge of galaxies increase. So the bulge to disk ratio is increasing. And therefore, if you do only one Cercic fit, I mean, you should most likely do a 2 Cercic fit, but if you do, you obtain something that is more and more weighted by the more and more dominant bulge. So you have a rise of the Cercic index as you go to higher stellar mass. However, you can see that you don't see that for the star-forming component. Okay, so to first order, the star formation activity happen in a disk, but it doesn't seem to happen into the bulge. Okay, so in a sense, you see a component of, you can explain the inside-out growth of the disk, because if you add the UV plus the infrared, you will have something that is slightly larger than the optical size. But you cannot understand in the main population the formation of the bulge. So you still don't know how the bulge is formed. Now, you can go a bit deeper and look at the distribution of galaxies, okay? And so here is a bit of a complicated plot, but let's say you can focus just on this axis, which is the ratio between the size of the stellar component and the size of the star-forming component. And here you can see that you have a Gaussian distribution, but you have a tail, okay, that is here. So it's not something that is simply the measurement. And this tail is telling you that you have in 15% of the galaxy star-forming components that are actually very, very small compared to the stellar component. Okay, so that means, yes? So here, the redshift is that you take all the redshift and up to redshift of 2.5, because then the MIRI is not a probe anymore of the near-infrared. Yes, and the way to mix together, it's by doing this renormalization. Okay, so you renormalize with respect to the mass-size relation to be able to put them onto the same plot. But at the end, again, you are looking at mostly massive galaxy. We are looking at galaxies that are above 10 to the 10, and the redshift distribution is peaking around 1.5. Okay. And so what we found is that 15% of this galaxy are, in a sense, in this cartoon. Okay. And if you look, we don't have a lot of statistics, and you can see, we see that the Cercic index of the stellar component is already slightly greater than 1. And also the B over A, and I will go back to that. So the axis ratio of this 50 galaxy is not flat and is peaking closer to 1. Okay, so it seems that you have a triaxiality of this stellar component, of this star-forming component. So in a sense, we have evidence, but it's still to be investigated, that you see in situ bulge formation in this population. And so, yeah, so we want to study that more. We just been granted the ANR that I coordinate to study this with more MIRI observation and to use more sophisticated tools to make this measurement in a way where we combine all the multi-wavelength observation together with SIGAL. Okay. So that was about the structural evolution of star-forming galaxies. So now I have only 10 minutes and I have two subjects, so I will have to maybe speed up a bit. So the next will be, what is the origin of red and dead elliptical? Okay, so there are the classic scenario to explain the formation of red and dead elliptical is to say that you have a major merger. And a major merger will have the properties to randomize somehow the angular momentum, and also to create a central compact starburst that will build also the bulge in situ and trigger at the same time AGN that will quench star formation, because you need to change the morphology and to quench star formation at the same time. So that is the classic major merger scenario. But you have also more and more people saying that at high redshift, the gas fraction is so large that you can have violent disk instability into this galaxy. And so maybe you have multiple phase of compaction that create the bulge in situ, maybe the galaxy that I showed before. And somehow, as you go to higher and higher stellar mass, you are in halos that are not able to accrete, and therefore you quench naturally by starvation. But you could also have like what people call morphological quenching. So when you have a large bulge, even if you have the gas is stabilized by the bulge influence on it. Okay, so how we can test that? It's very difficult, and unfortunately, I will not tell you how we create red and dead elliptical. It's still one of the big questions currently, but I will try to show you few results that we obtained in the last few years that tell us more. Okay, so about the quenching first, of course, now with ALMA and NOEMA, we can look at the gas content of this galaxy. So you could be quenched because you still have a lot of gas, molecular gas, but this molecular gas do not turn into stars. Why? Because of stabilization, or because it's too warm, or and so on and so forth. Or it's just because you don't have more gas. Okay, and so we can test that now thanks to observation with ALMA and NOEMA. And it's very difficult because those galaxies we know in the local universe do not have a lot of gas. And indeed, at high redshift, we don't have. So what we do is that we start from a complete sample of this galaxy and we stack. So statistically, we try to find the most constraintful upper limit on these galaxies. And this is, I think, currently the most constraintful observation that we have on a mass complete sample. And you can see that indeed, it seems that quiescent galaxies are quiescent because they don't contain a lot of gas. Okay, so their molecular gas fraction is about a fraction 10 lower than what you observe in star-forming galaxy. And now we can push that to quite high redshift. Okay. And now if you try to separate galaxies that have just been quenched or the ones that have been quenched for a long time, you see that even this is the case for galaxies that have been quenched only 500 million years. So that seems that the quenching happened relatively rapidly. But as I told you, the molecular gas reservoir of galaxy is also very small. So 500 million years is yet not very constraining, okay? Because even if you starve a galaxy in 500 million years, you have no more molecular gas. So you could be a quiescent galaxy. So now what are usually the people looking at quiescent galaxy at z equal 2, they have a scenario where the most star-forming galaxy, the most dust-obscure star-forming galaxy at z equal 4 must be the progenitor of this quiescent galaxy. And so what we could do now is to look at this very dust-obscure early star-forming galaxy at redshift of 4. And before with Hubble, they were barely detected. Okay, so we could not see how they look in the stellar component. And now with James Webb, that we are looking more and more in the near-infrared, where the dust is not so critical, we can look at how the stellar component of these galaxies that have been claimed to be the progenitor of quiescent galaxy, the so-called optically dark galaxy or optically faint galaxy. And so what we found when we look at those galaxies is that the most obscure massive star-forming galaxy, which we call the red star-forming galaxy, already have a stellar component that I show here that are as steep, so that means the same concentration than the one that we observe at the same redshift that we observe in quiescent galaxy. On the contrary, the ones that are blue star-forming galaxy, they look more like disk, extended disk. And so in a sense, that seems that indeed, if those galaxies are the progenitor of quiescent galaxy, they have already started their morphological transformation. They already have started to build these very compact stellar core that are the signature of quiescent galaxy. Now, how they build it? So again, then in that case, you have to look at the star formation activity of this galaxy. And again, that's become difficult. And what we want to see is that those galaxies look like bulge. So that means that you want to look at the star formation activity and whether the star formation activity is already triaxial. Okay, it's not like flat. So to have you can have a n equal 4 devocular light profile, but it could still be a disk. Okay, so what you would like to do is to take your galaxy, look at the star formation, and turn it. Okay, that's what you want to do. And if you are a disk, you turn its orientation compared to you. You will have an axis distribution that goes from 1 to 0. Okay, so if you are a disk, you have a flat axis distribution. Well, if you are a sphere, you can turn it the way you want. You will always have an axis ratio of 1. Okay. Of course, unfortunately, you cannot turn one galaxy. So what you want to do is to do a statistic of a galaxy population that you consider as being the same. And in a sense, the statistic is giving you the random orientation. And that's what we did. So we took ALMA observation of the brightest high redshift galaxy. And looking at this axis distribution, we could reconstruct how the star formation activity in this galaxy assemble. Okay, what is their triaxiality? Are they like disk or do they look already like triaxial object? And indeed, what we found is that the very high redshift galaxy, so redshift between 2 and 4, that have the brightest galaxy in the ALMA archive, when you do this game, what you found is that they already have star formation activities that happen to be triaxial. And so that's kind of the first time we see really in situ bulge formation in this disk. So in a sense, it seems that the morphological transformation doesn't necessarily happen ex situ. So that means by just you have two disks that come together and then you have like a different angular momentum and therefore you have this bulge formation, but you have in situ bulge formation. The only thing that is puzzling is that if you look at the morphology in James Webb of this galaxy, you found that they are not all triggered by merger. Some look like in the stellar component, they seems to be triggered also to be observed also in normal disk. And so this is still to be studied. And now, of course, I guess you have heard about Euclid. So this is one of the paper that was released yesterday or 2 days ago. It's by Fabrizio Gentile, who is working at CEA. And so Euclid allow you to have huge, very deep observation of the high redshift universe, and therefore to look also at populations that are in small field of view, very small. So, and you don't have enough object to really statistically extract the information. And so in particular, we know that it exists here. So you have your blue spiral, and here you have your red and dead elliptical, but you also have red spiral. So things that look like a disk, but do not have star formation activity. And you also have like things that have a large bulge and still have some blue-ish star formation, but they are a small population. But now with Euclid, you can analyze those populations with a high statistic and look where they are. And especially, we can look how they position in terms of stellar mass and density, so whether or not they are in field or in cluster environment. And what we found here is that if you look at your red disk, they basically appeared mostly in dense environment, and especially at low mass. And we think that it's due to ram pressure stripping. Okay. Well, if you look at blue spheroid, they do not appear really in the high density environment, but mostly at high mass. Okay. And that's tell you maybe that you have two different ways to transition from this blue spiral to this red and dead elliptical. Something happened in the field, so for most of the galaxy, where you first have the buildup of a bulge, maybe in situ bulge formation, that could then quench or not the star formation activity. And then in the high density, it seems that the ram pressure stripping is helping you a lot to strip the gas from this spiral, and then with minor merger, you will change their morphology. So we have to be careful that maybe you don't have only one route, and at least that's what the Euclid data seems to be telling us. Okay, and so I will finish. I have only 1 minute, so I will have to be quite fast, but what's happened at higher redshift? So at higher redshift now, of course, that's the territory of the James Webb. We can do a lot of things now with the James Webb, but we also have ALMA. And so we are, of course, extending with ever deeper observation with ALMA. We can look at the star formation rate activity also in the dust obscure form, thanks to ALMA, and try to expand what we're able to with Herschel and Spitzer. And we can look at the rise of the dust, cosmic dust density of the universe. And this is very important because normally, you have basically formation of dust by supernova that act very quickly in growth of dust due to the AGB star. And AGB star take about 1 to 2 gigayears to kick in. So if you look at the rise of dust in the first gigayears, you are sure that you are only looking at supernova effect. And therefore, it's very important to go to the very high redshift because you eliminate one of the gamer, and therefore you can constrain the effect of supernova. When we combine James Webb and ALMA, we can look now at the properties of the dust attenuation. I should have changed the IRX. And what we found is that the dust composition seems to be very similar at a redshift of 6 compared to what we observe in the local universe. So you have the normal relation between the beta slope, the optical slope, and the amount of attenuation in your galaxy. Now, I want to finish on that. I guess you have heard that one of the big surprise of the James Webb is to find a lot of very luminous or massive, depending on how you want, early galaxy. Okay, so very luminous in the UV compared to what pre-James Webb consensus on was. Okay, of course now you have a lot of models that have been developed to explain why you have such a luminous UV galaxy. And usually you have three different ingredients in your simulation that you can change. You can change the IMF to create more UV photon per unit star formation activities. You can have higher star formation efficiency, or you can have larger stochasticity. So that means the model where more flat star formation history. Now, if you create more stochasticity, you push some of the galaxy at the very bright end of the UV function. So how we can constrain that? What we did is, at least what we think we can bring, is that looking at the main sequence, the stochasticity, the dispersion of the main sequence is linked to the stochasticity of the star formation efficiency. So we look at the main sequence. It's of course very challenging. It seems that there is a main sequence, and we see that at a redshift greater than 7, you break down so you have higher stochasticity. Yet, if you take the dispersion of the main sequence at this redshift, you cannot explain the stochasticity that is needed to explain this very UV bright galaxy. So it's not enough. So in a sense, at a redshift of 10, the stochasticity that we measured is not enough to fit the model and pass in this data point at z equal 14. And what we also did is to go at very a lower redshift, and what we detect is one of the three most massive objects in the goods field. Okay, and they are so massive that if you take the most massive halo in the volume that you have probed, and you assume that you use the standard dark matter to baryon matter ratio, it seems that this galaxy, you are very close to have turned 100% of the baryon available in this halo into stellar mass. So you are not breaking the lambda CDM. Some people were saying, okay, at high redshift, you find very massive galaxies that break the lambda CDM. This is not the case. But you kind of challenge model of galaxy evolution. How you can have reached such a high star formation efficiency, so you turn a huge fraction of the baryon into stars so early. While we know that at lower redshift, this baryon to star to baryon is not as high. And so it seems that from these two simple observations that the higher star formation efficiency at higher redshift is favor. It doesn't mean that it cannot be the other one, but based on these two studies. Okay, and so I will leave you here. I think, as I said, the big outlook is, I think the role of environment will be very huge in the next few years. And why is because if you go into the most extreme place, this is the typical field of view deep observation that you observed, Cosmos field or the goods field on the backdrop of a normal simulation of dark matter. And you can see that if you want to probe all the environment, the super cluster at the center, the void, the filament, you need absolutely large field of view, okay, to really understand what is the effect of environment. And we are entering into this deep and large extragalactic survey, and you know more than me that the importance of Euclid. And so Euclid will not only deliver great cosmology, but I think it will have a legacy value also for what they call the legacy field. And I think here it will play a big role. And of course, SKI is coming to complement that for the star formation activities. Okay, so I will stop here and I will take your question. And sorry if I'm a bit late.
Yeah, so time for question. Nikos?
Thanks indeed for the very nice talk. I have two short questions. At some point, you mentioned the role of outflow. You showed that in the equation you showed. But from the observations you mentioned, I did not see any need for outflow. So my question is, how do you think that the observations imply about the outflow?
Yeah. So the outflow, I think in the equation, usually they are not so important. So when you do the differential equation, but of course you can always counterbalance one by the other. Observationally, we know that there is outflows. If you look at lower stellar mass, you see outflows with broadline emission that we associate with stellar feedback. But those outflows are not so energetic and do not transport so much mass. So the mass loading is not so large. And therefore, we believe that it's kind of this fontaine. So, I mean, you explode, so it's kind of delay and smooth out your star formation activity. At the higher mass, outflows are needed by people doing simulation and by Johan, I guess, to explain. And observationally, we don't see them.
That was my question about observations, not the theory.
We don't see them, but to be honest, we cannot say to the simulation that they are wrong because it's very difficult to see them because I mean, you can easily see them in the ionized form, and we see outflow in the ionized phase, but you also need the molecular phase, the atomic phase, and I think we don't have all this brick yet.
Okay.
And the problem also is that I mean, the AGN have a duty cycle that is very short. And so somehow it's difficult to see, to associate AGN and outflows that you observe. It might not be on at the same time in a sense. So you have to be, yeah. So it's difficult.
Okay, yeah, thanks. And the second short question is about the molecular gas.
Yes.
You mentioned also the relationship between star formation rate and molecular gas,
yes.
not atomic gas.
Yes.
But when you showed all those relations about the size of the disks, the gaseous size,
yeah.
It's what kind of gas? It's molecular?
So all the gas is molecular here.
All
so
molecular.
Yes.
Okay.
So and it's even worse than that. So we measure the dust. Okay. So we measure the dust and then we assume a gas to dust ratio. So to measure the gas, even at high redshift with ALMA or NOEMA, that are fantastic machine, you need between 30 minutes to 1 hour per galaxy to measure the CO line. So if you want to do statistics with thousands of galaxies, what we do, the trick is to observe in a dust continuum, and we assume that the dust and the molecular gas are always together, which is observe locally, and we do that. Now, why we think the atomic gas is not so important, at least for the star-forming budget, is because the density in those galaxies are way larger than when you observe in the local universe the transition between the H1 to the H2. So the surface density of gas is at a place where you don't expect H1 to be. Of course, H1 can be in the reservoir and can help us to understand where is the reservoir. Is it coming from the cosmic web or from actually the intercluster medium or the halo?
Yeah, very nice talk. There is something you have not talked about is which process controls the dispersion.
Yes.
And of course, you mentioned many times that the main sequence is very well defined, so that makes the dispersion more interesting.
Yes.
All these objects. So what can you tell about this?
Yeah, so I mean, there were some attempt to do that. So for example, I did something that I never published, but some other people did it also. So for example, you can look at the dispersion that you measure with H alpha. So H alpha is kind of a 10 million years star formation proxy because it's really looking at the nebular line at the H2 region. And then when you look in the UV or in the far infrared, you are looking more at star formation average over 100 million years. So if you look at the dispersion, the H alpha is slightly larger than the one in the UV plus infrared, and that you can interpret that by the stochasticity. So you can do model and description of the model. So you parameterize your star formation history as something that vary, and you can do kind of the Fourier transform of this. So we believe there is a lot of information hidden in this dispersion, but it's still very difficult to interpret because, of course, you can increase the dispersion in the H alpha just because your conversion factor is wrong. And therefore, you always have like problem between, is it something that come from my calibration, from my systematics, or is it something that is real? And I think not a lot of people have dared to go very, very far into the interpretation of this. But there is a lot of science to be done here, but it's a difficult one.
Thanks for your talk. Since we talked about outflows, I want to ask you the other question is about fueling. I mean, you said it was very important to bring material into the galaxies, but observationally, that's very, very complicated.
Yes.
So do you have any prospects about
how to look at this? So, so recently with Magnelli, we were looking at, he was looking at Lyman alpha emission, for example, and he was looking at Lyman alpha halos that could look like filaments, and so on and so forth. But it's a very tricky business because, of course, Lyman alpha is a resonance line, so it can be coming from photon different. But so it's something difficult. The prospect. Obviously, the H1 can help us quite a lot if you go to higher redshift because maybe you can probe the phase that is a bit around the galaxies. Stacking can help us, but yeah, it's going to be difficult. So that's why we say, I mean, people doing simulation tell us, I mean, there is this accretion. I mean, that's fine, but that's good. But we need to probe it observationally. I think there is some SZ effect that you can do stacking between filament, and you can see and probe this gas. And so, in a sense, so far, in my point of view, the fact that the molecular gas reservoir is small is not a direct proof that you need accretion, but it's kind of the strongest and direct proof of this.
Thank you.
I just wanted to follow up on that question. Do you know anything about ALMA 2040 and whether that would help?
So, ALMA 2040. So I've been a bit involved, but I'm also involved in Atlas, so which is not a concurrent. I mean, we can discuss politics if we could do one united. The thing is that it's depend on which phase is this gas, and it's most likely not in the molecular phase, or you will see something and you will have to distinguish between, is it the fontaine coming back from a previous outflow? So it's going to be difficult. I think it's for that. So the molecular phase, which is the one, but of course you can go to the atomic, and people doing, I mean, maybe I can see Pierre that's doing BCG, or people looking at nearby, they can give us clue of how to detect this and how to disentangle this different phase, in which phase is it, and what are the proxy for that. Yeah.
And I have a second question. So you measured at some point the historicity index of the star forming region and of the stellar component.
Mm-hmm.
Did you ever compare these indices to the thickness of the gaseous disk, just to see whether the star forming component is indeed aligned with what you would expect to be forming out? So if you make like a profile of the, for example, the molecular gas, is it like well aligned? Is it the same structure as the star forming region or not?
So it's the first time that we managed to do the star formation profile. So we have a ALMA large program that is supposed to do this kind of study. So on a sample of, I think, 20 galaxies, where we will be looking at having a holistic view of the stellar component. We have the CO, and we will have the dust, and therefore we will be able to do a bit all this study. But it will be, even if it's called a large program, and maybe we have a former ALMA director here, is that a large program of 150 hours, even though it's a fantastic machine, and I understand that they don't want to do much more, it's still very limited. So in a sense, you will need several large programs to answer this question, and 1,000-hour large program will be good also. Legacy, community-driven. Why not?
Pierre, je crois que Pierre, ok, comme tu veux.
C'est moi d'abord.
Yeah.
So thanks, Benjamin. It's a great work. I'm very impressed. I have many questions, but I'll talk about one. So you talked a lot about the understanding the dispersion of the main sequence of star formation rate versus stellar mass. And a quick comment: your figures also show that the starburst galaxies seem to be disjoint, starting from redshift 0.5. I was very impressed.
So there's disjoint. The problem is that it's very difficult in the as you go to higher redshift, you have what we call the ladder of star formation indicators. So
yes, so
you do the best as you can. And that creates also discontinuity a bit, because you go from air shell plus UV to MIPS plus UV to just UV. And it's changed a bit. Okay, so it could be. But yeah, normally what we believe is that if you analyze the slice, you see a Gaussian distribution, which is the main sequence, and you see another Gaussian distribution underlying, that is the starburst. That's kind of the rationale before that the fact that starburst exists in a sense.
Because the time scale for the starburst will be, if it's a gas-rich merger, for example, then that will be maybe a bit longer than you might expect. So you might expect more continuity in this figure. But so we'll move on to something else.
Yeah, okay.
because my time is short.
Yes.
Can we look also at, you mentioned the depletion time is roughly independent of redshift.
It's actually moving, but
so I would like to see more about the depletion time. How does it vary with stellar mass? And how does the dispersion vary, and what can we learn about it?
So I can show you. So here the different color are different stellar mass.
Okay.
And you can see the leverage is not huge, and because I mean this you basically take the Cosmos data points, so from Henry catalogs, and then you go everywhere in the archive and you try to find something in ALMA, and you stack thousands of projects in ALMA in the UV. So it's very challenging to do, and you obtain this detection which are there but are difficult. But so what we found is that it doesn't change too much as a function of the stellar mass, but it changes a bit as a function of the redshift. But it's always below 1 gigayears. The change as a function of the redshift is actually understood the fact that the Schmidt-Kennicut relation, not law, is a bit superlinear. Okay, and so as you go to higher redshift, you go to higher surface gas density, and therefore you go to slightly higher star formation efficiency, and therefore slightly lower the depletion time.
And the depletion time is independent of your resolution. That means if you look at molecular clouds, will you have the same depletion time?
Yes, no, you're totally correct here. I mean, at some point, star formation and molecular gas must be different. So you have a scale where they actually totally decoupled in a sense. So here we are. This is what I like to call blobology.
Yes. Yeah.
I mean, this is complete blobology. So I have no idea, and so that's why I mean So the understanding, for example, in the BGL paper at the scale of kiloparsec, we think that what we see is that the Schmidt-Kennicut relation is very close to actually a slope of 1. Because of exactly this reason is that you have a universal brick, but within your kiloparsec you cannot distinguish them, and so you simply count the number of elementary brick that you have within your beam, and so therefore you have a slope of 1 because you cannot resolve the real Schmidt-Kennicut law.
Okay, thank you.
I have 2 questions. The first one is at some point you separate the star forming components and the stellar component. It's in the same galaxy.
Yeah.
And how do you do that? It's just color information, or?
Yeah. So that's good because that also motivates my ANR. So the way we do is to for the stellar component, you simply take the rest near infrared image, the closest to, let's say, 1 micron, where at 1 micron, we say that you have more or less a constant ratio between the amount of photon that you receive and the stellar mass. Okay. And then you look at the profile, you measure the size, you measure the position angle, you measure everything. And then for the star forming, what I call star forming is a bit of so it's a proxy of star formation. It's the infrared emission. So that means you look in the mid-infrared with MIRI. You're actually looking around, let's say, 10 micron rest frame. And we use the fact that at 10 micron, you have a linear relation between the amount of 10 micron photons that you receive and the star formation. It's not totally true, of course. It has some caveat, but that's basically the proxy that you do. Now the ANR is to say, okay, you can do better than that because you have many, many different bands at many different resolution. But so you can try to synergetically, that's what I use in the proposal. So I use this word, all this image together. We using a SED fit where you fit the stellar component, the star forming component, to be able to extract this information a bit better by combining all this information at the level of the map. And so to use a code that is named CGAL that does that for catalogs, but now we want to do it at the map level. So we call that CGAL 2D. Voilà.
Okay, thank you. And my second question was on ALMA observations. So you have a population of galaxy observed in the main sequence.
Yeah.
And then you observe with ALMA to trace the gas. But was a fraction of galaxies observed with ALMA?
So here, so we do 2 things. So you can do this approach, which is you know the galaxy and you ask for ALMA to observe the gas, but it's very expensive. So what we did is to say we need thousands of hours. No time allocation committee will give me 1,000 hours. So I sit and relax, and I wait for people to ask for all their observation into Cosmos. So you have a field of view that everyone is the favorite field of view. It's Henry's favorite field of view. That's Cosmos. Okay. People are looking at galaxies, at image. And in this image, you have, of course, a central object that people have been studying, but you also have area around. And the photons have been received from this region. They are not necessarily detected, but statistically, you can take your package of galaxy at a given redshift and stellar mass and go into the archive and look at all this line of sight and statistically combine them to try to measure this. That have the advantage that you don't have to convince a TAC, that you can use synergetically all the archive again, and you can have a kind of unbiased view of the galaxy population. If you detect one galaxy, you will have an average that is the average divided by root square of 1. I mean, the error on the average. If you have does that on 1,000 galaxies, you might not detect them individually, but your average is actually more accurate. And I try to convince the TAC to do non-detection thousands of galaxies and to have a detection when you combine them, but they don't like this idea. But maybe I try again. Yes. I mean, I know that people are doing that with Apex now, so.
I suggest we stop here. If it can be short, Christophe.
To address the question of the tightness of the star formation main sequence, on Monday, I'll give a talk explaining this in terms of spiral structure.
Okay.
Thank you.
And do you give this talk here or? Okay.
Let's stop here and thank Benjamin again.
Thank you.